welcome you to this session of thermodynamics. In the last session, we discussed that if two engines operate between the same temperature limits, one is the temperature for heat addition, another is the temperature for heat rejection. If one is a reversible engine, its efficiency is higher than that of an irreversible engine. And a corollary to it is that all reversible engines operating between the same temperature limits have the same efficiency. So this thing we discussed and proved logically, but I think there was little confusion in its understanding through logic. That's why I will repeat this thing again, this proof. I will repeat this thing again. You see that there are two thermal reservoirs. One is at temperature T1, another is at temperature T2, T1 greater than T2. And we know that two temperature reservoirs are essential for a heat engine to operate, to develop work in a continuous cycle. Let us consider one reversible heat engine which takes heat Q1R, this subscript R is used for reversible engine, from this temperature, high temperature reservoir source T1, and it has to reject, according to thermodynamics second law, the amount Q2R to the thermal reservoir T2. While doing so, it develops and work WR. Here also it is written WR, which is equal to, from the first law of thermodynamics, that is energy balance, Q1R minus Q2R. Second law tells that Q2R cannot be 0, there has to be Q2R. That is the only restriction, but first law is always valid like this. And we consider another heat engine working in a continuous cycle, which is not a reversible heat engine, which draws an amount of heat Q1, which we set deliberately for the proof equals to that of the Q1, that of the heat taken by reversible engine, that means Q1R. And obviously, since it is an irreversible engine, it will reject an amount of heat which is different from that. If the heat addition and rejections are same, the work quantity will be same by the first law. You know, out of these three quantity, heat addition, heat rejection and work, two are independent, one is dependent by the conservation of energy. So they cannot be same for a reversible engine. When it is an irreversible engine, they have to be different. That is the very first logic. So let us consider that it rejects Q2, which is different from Q2R, and while doing so, it develops an work W, which equals to Q1 minus Q2. I think this is okay. Now we have to prove that. Now what is eta first of all? Now eta, by the law of conservation of energy, by definition of eta is what? Work for reversible engine, work developed by the heat added. All right. And what is eta for this irreversible engine, which is a natural engine? W by, now this is Q1R, and it will be also Q1R, since Q1 has been set to Q1R. Now we have to prove that eta R is greater than eta, to prove, to be proved. Now what we do to prove this, we first assume that eta R is less than eta. We first assume that. And then we prove that this is not possible. How? If eta R is less than eta, then what we get? Eta R is less than eta means WR is less than W. Eta R is less than eta, Q1R is same, so WR is less than W. Or we can write other way, W is greater than WR. Now what we can do, just see here, that is the most important thing. If this is a reversible heat engine, all the processes can be reversed. Reversible heat engine means that all the processes are reversible processes. So all processes can be reversed without any other change in the surrounding, according to the requirement of a reversible process or characteristic feature of a reversible process. That means if we reverse all the processes of this heat engine, it will act as a heat pump. So it will act as a heat pump. I am sorry, this will be, oh sorry, this is all right. Reversible heat pump, I am sorry, reversible heat pump HPR, which will boost, if this reversible heat pump is allowed to operate, then it will give the same amount of heat Q1R in T1, which is used to take while acting as an engine, and it will draw the same amount of heat Q2R from the reservoir T2, and it will demand the same amount of work which it delivered WR to the surrounding in case of an engine. That means this work and heat quantities interactions are equal in magnitude but opposite in direction. That is the characteristic feature of the reversible heat engine. But if we reverse this heat engine, it will work as a heat pump. Don't consider that as it is a irreversible heat engine, it cannot be made to operate as a heat pump. In that case, the directions of the heat interactions will be opposite. Definitely the work interactions will be opposite. It will draw work, it will give heat. In that case, the quantities will not be same, which means that if it has to elevate heat or pump heat Q1 to the temperature T1, it may not draw the work W from the surrounding, it may not draw or it may not take the heat Q2 from this T2. That is the difference between a reversible and irreversible engine. So therefore, it is always useful for us to prove this thing, to make this reversible heat engine to operate in a reverse direction as a reversible heat pump, so that the quantities reveal the same magnitude but in the opposite direction. Now we know, we have assumed that eta R, the efficiency of the reversible heat engine, is less than eta, which means the work developed W by the irreversible heat engine is more than that of the work developed by the reversible engines WR. So therefore, in this case what we can do, we can couple these two so that the work developed from the heat engine can be utilized to drive the heat pump, and in spite of that we get a net amount of work W minus WR as the work output. And since these two heat quantities are same, they can be joined by a diathermic wall. That means this reservoir is redundant. That means the working fluid of this heat pump will act as the thermal reservoir for this heat engine, and the working fluid of this engine will act as the thermal reservoir of this heat pump. That means the heat rejected by this heat pump will be delivered to this heat engine as the addition of it. So therefore, the entire system corresponds to a machine which interacts with only one thermal reservoir. That means a thermal reservoir of a single fixed temperature and developing a network, which is not possible, and violation of Kelvin-Planck statement. This is violation of Kelvin-Planck's statement of second law. So therefore, the only opportunities are, now this is not possible. So therefore, there are two possibilities, eta R greater than eta or eta R is equal to. Now the logic is that eta R cannot be equal to eta, because an irreversible engine and reversible engine are different. So their heat interactions and work interactions are different. So that when you reverse it, it will not reveal the same magnitude. So therefore, it has to be a different engine than that of the reversible one. So we discard this logic. These two cannot be equal. Either this will be greater or less than this. That means these two will be different. So with this logic, we can prove that the only go is that eta R is greater than eta. It is clear. Now the next step is that if both of them are reversible, then they are of equal efficiencies. That means the next corollary to this theorem is that if there are a number of reversible engines operating between the two fixed temperatures, their efficiencies will be same. They cannot be different. How to prove it? Now the same thing, I am not going to a different drawing. Now consider both the engines are now reversible. I am not giving this subscript 2R, WR, then it will be more congested because then R1, R2. So let us consider this Q2 is the heat rejected by another reversible engine, W is the work developed by another reversible engine. So we consider two different reversible engines, and we consider similar way that first eta R is greater than eta. That means efficiency of this reversible engine is greater than this one. Now in this case, I consider this machine also as a reversible. That means eta is the efficiency of a reversible engine, that is the engine at the right to me. Okay. Now in this case, as I have shown, I can reverse this one and prove that it is not possible. Now since it is a reversible engine, in the next step I can reverse this one and can get these quantities exactly in the same magnitude, because which I could not do in the earlier case, but now I can do it because it is also reversible. That means Q1, that means Q2. Now, when I assume this eta r is greater than eta, I reverse this one. When I assume that eta r is less than eta or eta is greater than eta r, then I reverse this one. If I reverse this one, then when eta r is greater than eta, then what happened? To be proved, sorry, eta r is less than eta, when I assume this, sorry, eta r is less than eta, then W was greater than WR. And in that case, I reverse this one. Now now I will take eta less than eta r. Not eta r less than eta, eta less than eta r. That means WR is greater than W. In that case, I will reverse this one. You understand? First I consider eta r, this one is less than eta. That means W is more than WR. Okay? So I reverse this one and we prove that this is not possible. Now I consider eta less than eta r and I reverse. When you consider eta less than eta r, means WR greater than W, I reverse this one. Now here, since it is also a reversible engine, at the beginning we have considered here, the both are reversible, then I can reverse it, and in a similar manner I can prove there is a work, because WR is more than W, net work WR minus W, coming out of these two, we can couple these two. That means this will remain as a heat engine. In that case, we can couple these two and we get the work, which is violation of Kelvin-Planck statement. That means we prove neither eta r less than eta nor eta less than eta r. That means the only possibility is the eta is equal to eta r. Try to understand the logic, so that if two are the reversible engines, then if I assume first that one of these engines, for example eta r, is less than this, then I reverse this engine and prove that this is a violation of Kelvin-Planck statement. In another case, if I consider this is less than this engine, the efficiency of this engine is less than this one, then I reverse this one and I can prove that the equivalent one is a machine which interacts with a thermal reservoir at a single fixed temperature and developing a network, violation of Kelvin-Planck statement. So only opportunity is eta is equal to eta r. So I think logic is convincing, but it is not at all essential to memorize this thing, because nobody will ask you for this, how do you prove it, but it is extremely important to know this theorem throughout the course of thermodynamics, wherever you go, even at the higher level, that therefore, what is this theorem? That if there are two thermal reservoirs at different temperatures, T1 and T2, a heat engine will operate. It will take heat from the higher temperature reservoir and will reject heat at the lower temperature reservoir, and will operate in a continuous cyclic process and will develop work, which according to first law of thermodynamics will be the difference between the heat added minus heat added and the heat rejected. This is number one. Number two, if there is a reversible engine operating between the same temperature limits, then its efficiency is the highest among all other engines, all other irreversible engines. And next, all reversible engines have the same efficiency if they operate under the same temperature limits. That means the efficiency of reversible engines is unique when the temperature limits are prescribed, and this acts as the maximum performance criterion or the ideal value for any natural engine. That means the efficiency of any natural engine. So at the same time you can think that is true that all natural engines will be having different efficiencies operating between the same temperature limits. Even the maximum of these efficiencies is lower than the efficiency of a reversible heat engine operating between the same temperature limits. So with this, I will go to a very interesting thing, that concept of absolute thermodynamic temperature scale. Concept of absolute thermodynamic scale of temperature. Thermodynamic scale of temperature. Okay, absolute thermodynamic scale of temperature. Now, so far what we have read, if we have a thermal reservoir at any temperature T1 at any conventional scale, let us consider Celsius scale, and if there is a heat engine which is a reversible one, HE, if there is a reversible heat engine and it takes Q1 amount of heat, now this is the block diagram of any heat engine. Now we know that the efficiency of a heat engine, reversible heat engine, is fixed when the two temperatures are fixed. When the two temperatures are fixed, the efficiency of a reversible engine is uniquely fixed. That means all reversible engines have the same efficiency. The second part of the Carnot's theorem, which can be expressed mathematically, that efficiency of a reversible engine, I can give this R, is therefore a function of these two temperatures. All right. Now, how do you define the efficiency? Now, in this case, efficiency will be, in all cases, efficiency is defined by the unique manner, that is work done by heat added. Now, I am not using the subscript R. Okay, let us use the subscript R for your understanding, for a reversible engine. Now, the efficiency is same for reversible or irreversible engine. It is the work divided by the heat added. And similarly, the work is the difference between the two heat quantities. It is also same for both the engines, because it is the law of conservation of energy. So, there is no restriction for friction and other conditions, that irreversibility. So, therefore, it is valid. You have to remember that. In this case, Q1R minus Q2R by Q1R. So, we can write 1 minus Q2R by Q1R. So, therefore, we see that eta R is a function of temperature T1 and T2, from which we can tell, this is a very important conclusion, that the ratio of the heat interactions, I write in this fashion, it looks nice, that heat added to heat rejected is some function of two temperatures. It is a very important conclusion, that the ratio of heat added to heat rejected is a function of two temperatures. So, the ratio of the heat interactions, Q2R or Q1R also, that means the ratio of the two heat quantities of interactions by the reversible heat engine is a function of temperatures. This is valid only for a reversible engine. For irreversible engine, it is not so. This is because for irreversible engines, if T1, T2s are fixed, different irreversible engines will depict different efficiencies. It is because of the fact that all reversible engines have the same efficiency when T1 and T2 are fixed. That means the efficiency of a reversible engine is a function of the two temperatures only. Now, we will exploit this to define the thermodynamic scale of temperature. At this moment, we do not know anything about this functional relationship. We can only express in an implicit form like this, that some function of T1 and T2, unknown function. But let us utilize the concept of heat engine to go one step further to give some particular form of this function. What is that? You remember this, then we construct this. Let us consider a reversible engine. There are three temperatures. One, now here all reversible engines, I am not using subscript R. So, one reversible engine is heat engine 1A, which takes heat Q1 from a thermal reservoir T1 and rejects heat Q2 to a thermal reservoir T2. Sorry, T1, small t1 you give, because now it is a conventional scale, let us consider a Celsius scale. So, therefore, T1 has to be greater than T2 and it develops an work WA, which must be equal to Q1 minus Q2. Now, we consider another heat engine which takes this heat Q2 from this thermal reservoir. That means this thermal reservoir is in contact with both the engines. So, this heat engine B takes this heat Q2 from the thermal reservoir T2 and deliver or reject heat Q3 at another thermal reservoir T3, where T3 is less than T2 obviously, and it develops the work WB, which is equal to Q2 minus Q3. All right. Now, according to this relation that the ratios of heat interactions are the functions of temperatures, we can write for the heat engine 1 Q1 by Q2, all are reversible engines. So, I am not writing this subscript R anymore, is equal to what? Some same function of T1, T2. For the reversible engine B, what will be? What it will be? Q2 by Q3, and it will be equal to the same function with the argument changed, because here the temperatures are T2, T3. Same function F. Now, if we consider these two heat, now we can remove this reservoir, because we can use this, you can make these two heat engines connected, so that the heat rejected by this heat engine will be taken by this heat engine B. That means the working fluid of heat engine A will be the source or thermal reservoir for the working fluid of heat engine B, and the vice versa. So that we can get rid of this, we can connect this. I am not drawing this as a separate figure. In that case, the combination of A and B, these are known as heat engines in series, will be an equivalent heat engine developing an work of WA plus WB and interacting with thermal reservoirs T1 and T3. That means they are taking heat, that means the equivalent engine is taking heat Q1 from T1 and rejecting heat Q3 to T3. For that equivalent engine also, one can write Q1 by Q3 is the same function T1, T3. Now, this gives a further clue to the type of this function. We may not know this function explicitly, but at least a type of the function is known, the particular type. How? We can write this, if you see the left hand side, we can write this function of T2, T3. Q2 by Q3 is what? How to write it? Q2 by function of function, rather I think it will be better if you write this way, function of T1, T2, that will be better, becomes is equal to Q1 by Q2 means what? Q1 by Q2 means this divided by this, that means function of, anyway you can write, there are various ways you can write, this is now very simple, is the function of T2, T3. That means Q1 by Q2 is Q1 by Q3 divided by Q3 by Q2. Anyway, we can write Q2 by Q3 also, the similar way, this into this. So, if we write this way, then we see that the function should be such that the function of T1, T2 must come out as the quotient of the two functions, one is T1, T3, another is the function T2, T3. So, what is the alternative? So, the alternative is this, it can only happen if and only if this function can be expressed as a function of T1 and T2 like this in terms of quotients, so that it cancels out. So, this is very, very important. Wherefrom it comes that if this has to be true, this is only possible if this functional relationship is of this form, function of T1 by function of T2. That means if it is can be expressed by this, only we can get this relationship. Any of these combinations will give like this, provided this becomes a function of T1 by function of T2. Clear? Okay, very good. Now, this is the base. That means first we started with that the heat interactions by a reversible engine between the two thermal reservoirs is a function of two temperatures. Then we came to a conclusion using two reversible heat engines in series that this function will have a shape like this. That means the type of function will be like this, that functions of T1, T2 should be a function of T1 divided by another that function of T2, same function. This function ultimately is declared as the absolute thermodynamic temperature scale. That means this function itself, this is a function of temperature only, is defined to be the absolute thermodynamic temperature scale. So, therefore, the absolute thermodynamic temperature scales are defined. So, what is FT1 by T1, T2, it is Q1 by Q2. So therefore, what we get Q1 by Q2 is T1 by T2. Now we see all these functions are defined as the quotient. That means this is phi T1 by phi T2. Similarly, this function will be phi T2 by phi T3. So this function will be a function of T1 by function of T3. So these functions are defined as the absolute thermodynamic temperature scale. That means the absolute thermodynamic temperature scale is declared to be that function of the temperature. This may be in any conventional scale, which means the basic definition of absolute thermodynamic temperature scale or absolute thermodynamic scale of temperature is this one. That means it is such the ratio of these two temperatures is equal to the ratio of the heat interactions by a reversible heat engine. So immediate question comes, sir, then how do you fix this temperature? How do you determine this temperature? We cannot have any reversible engine in practice. This is an ideal abstraction. Yes, its basic definition is like this, but afterwards we will see that the heat interactions, the ratio of heat interactions by ideal heat engines can be expressed in terms of other properties, other measurable properties through which we can ultimately determine in practice the absolute thermodynamic temperature scale. And afterwards it will be shown that this absolute thermodynamic temperature scale, which we now define in following the second law of thermodynamics, is exactly same to the ideal gas temperature scale, which you have already read. Ideal gas temperature scale, they are identical. That will be proved afterwards, but now we learn that absolute thermodynamic temperature scale or absolute temperature on an absolute thermodynamic scale is such that their ratios equals to the ratio of the heat interactions by a reversible heat engines connected between these two temperatures. That means if a heat engine is connected between two reservoirs, and if we want to designate the temperature of the reservoirs by absolute thermodynamic temperature scales as T1 and T2, then the ratio of T1 and T2 will be the ratio of Q1 by Q2 by the heat engines. So here also you see, like your internal energy definition came through its difference, not in absolute value. The difference of internal energy is the heat and work interactions, net heat and work interaction by a system in a process. Similarly, the definition of absolute thermodynamic temperature scale has also come through its ratios, T1 by T2. Now with this, you can write that if there is a reversible engine, again the same thing, it will be little boring at this moment. Now if I denote the temperatures as the absolute thermodynamic and you consider a reversible engine and giving heat T2, we can now write Q1 by Q2 is T1 by T2. Now what is this efficiency? W is Q1 minus Q2. What is its efficiency? Eta is W by Q1, 1 minus Q2 by Q. Now this is valid for all engines. There is no restriction. It is the definition of efficiency, and then this part is the definition of efficiency, and this part is the first law of thermodynamics. But for a reversible engine, if it is reversible, we can write which means that the efficiency of a reversible engine working between two temperature limits T1 and T2, where T1 is the temperature of heat addition and T2 is the temperature of the thermal reservoirs where heat is being rejected, is given by the efficiency of the reversible engine is given by 1 minus T2 by T1. This is the efficiency of all reversible engines which operate between the two temperature limits. T2 as the temperature of heat addition, T1 as the temperature, rejection, T1 as the temperature of heat addition. Here one question comes which will be cleared later on, that in case the temperature is not constant during the heat addition and heat rejection process, a reversible engine not necessarily always has to take heat at a constant temperature. There may be a variation in temperature. There may be a variation in temperature while heat is added and while heat is rejected. In that case, this will be treated as mean temperature of heat addition. That means 1 minus mean temperature of heat rejection by mean temperature of heat addition. This will be cleared afterwards. But at the present moment, we learn through a very simple case that let us consider the temperature of heat addition is constant. That means isothermal heat addition process, isothermal heat rejection process. And this is a reversible heat engine. So therefore, efficiency is 1 minus temperature of heat rejection minus temperature of heat addition. Clear? But this is not true for a irreversible engine. We cannot write, we can write only this, because this relationship is not valid for an irreversible. For a heat pump or refrigerator, HP or refrigerator, I am not writing the full. It is other way, it is giving heat, elevating heat to a higher temperature. Here what happens? T1 is greater than T2. Here also same thing, T1 is greater than T2. It draws work from the surrounding in doing so, which again, according to first law, what it will be? W will be Q1 minus Q2. Same thing, or Q1 is equal to Q2 plus W. It is written this fashion so that this is manifested that work is being converted into heat. So that we write Q1 is Q. This is a convention. Here we do not write W is Q1 minus Q2. Same thing you can write, because it is the conservation of energy. Okay, you understand? So this is the way as a heat pump or refrigerator works. So COP of a heat pump is defined for any engine, reversible or any machine, reversible or irreversible, as its performance, that is how much heat is being elevated at high temperature divided by how much work it takes. Similarly, COP of a refrigerator is, the denominator is the same, numerator is changed, because this is the heat, how much heat is being taken from the lower temperature divided by this. These two are the definitions. Now from first law, we can write this Q1 divided by W is Q1 minus Q2. Similarly, Q2 divided by Q1 minus Q2. And one important relationship comes from this, that COP of a HP is 1 plus COP of a refrigerator. That is a very simple thing. I am not doing that because this is so simple, because this is the definition I already told earlier, that COP of a heat pump is Q1 by W. COP of a refrigerator is Q2 by W. With reference to this figure, Q1 is the heat elevated to higher temperature, Q2 is the heat rejected, taken from this temperature T2, lower temperature. So a same machine works both as a heat pump, also as a refrigerator. When our attention is here, it is heat pump. When our desired objective is this one, taking heat from a lower temperature, is refrigerator. So COP of an H pump is defined like this. Then by the principle of first law of thermodynamics, Q1, W is Q1 minus Q2. So these are the definitions. And COP of a heat pump will be 1 plus COP of a refrigerator. That means COP of a heat pump minus COP of a refrigerator will be 1, because if you subtract this from this, you will get 1. But now I come to a case of COP of a reversible heat pump. You understand? COP of a reversible heat pump. This will be T1 divided by T1 minus. This Q values may be replaced by T values, because Q1 by Q2 is T1 by T2. Similarly, COP of a reversible, here I write COP of a reversible COP of a reversible refrigerator is equal to T2 by T1 minus T2. That means this definition of COP in terms of the temperatures are valid for reversible machines. That means reversible heat pump and reversible refrigerator, like the reversible engines. So that this means that ratios of Q's can be substituted in the ratios of the temperatures. That is as simple as this. All right. Now, a little bit conceptual thing I will discuss, that so many things we have learned through a reversible engine. But how to conceive a reversible engine? First, Carnot gave an idea that how we can achieve a reversible engine. Now, thing came like that. So many things were developed by physicists about the reversible engines and ideal performance, and everybody knows that reversible process is the ideal process where the dissipation is nil. So a reversible cycle has the highest efficiency amongst all irreversible cycles. After knowing all these things, Then an engineer started thinking how to achieve an engine very close to a reversible engine. When you know that reversible engine or reversible cycle is our ideal performance criterion. So therefore one has to reach. So therefore the thought process started evolving that how one can go very close to a reversible process. So it was Sadi Carnot, he was basically an engineer. He was basically an engineer and physicist, of course. He first developed a concept by which one can visualize in practice a reversible engine, and that engine was named as Carnot's engine. So let us consider that first. That was named as Carnot's engine. So Carnot's was the first, Carnot's engine. Carnot's engine. This was the first, the concept of a reversible engine was first given by Carnot, Sadi Carnot. He was probably a French, he's an engineer, he's a mechanical engineer, and then converted to a physicist. Then Carnot's engine. This engine consists 4 processes. Just to write first the process. One is the reversible, all processes. This is a reversible engine. Carnot's engine is a reversible engine. 4 processes. One is reversible isothermal, reversible isothermal, reversible isothermal process of heat addition. Reversible isothermal process of heat addition. He conceived a reversible isothermal process because it is very simple to conceive. Because what is the criteria of a reversible heat transfer, addition or rejection? That the temperature difference between the 2 systems interacting heat will be 0, but this is not possible. So always I told, earlier also I told that a reversible process means there cannot be any process. So therefore in a limit a reversible process can be thought if the temperature difference can be maintained infinite small. So it is always easy to conceive that both the system and its surrounding maintain the same dt throughout, and to do it both the system and the surrounding has to be at constant temperature. So therefore it is always better to conceive a isothermal process of heat transfer to be a reversible heat transfer process. Otherwise what will happen if you consider the process to vary with the temperature, which happens with a finite body. When it gives heats or loses heats, its temperature varies, then always you will think of an infinite number of reservoirs, as I explained earlier, for reversible heat transfer process, so that always system and surroundings will have to be in contact with each other through an infinite small temperature difference. That is the reason for which an isothermal process of heat interactions, heat addition or rejections have been thought of as an irreversible heat transfer process. Nevertheless, the process where the temperature varies is not a reversible heat addition, heat rejection process. Many students, or even not students, many people have these confusions, that always think that for a heat addition process to be reversible or heat rejection process to be reversible, it has to be isothermal. No. So this is because of this fact that it is easy to conceive. Carnot initially thought that the process of heat addition should be isothermal and reversible. Isothermal process also does not mean reversible. These are the concepts I am telling in thermodynamics, because all these things are written in the book. That for example 2 systems are there, heat is being transferred from one to other and they are maintaining same temperature. System temperature is T1 and the surrounding temperature is T2. And while receiving heat, system is at constant temperature T1, surrounding is at constant temperature T2, but there is a finite gap T1 minus T2. So it is not a reversible heat transfer process. So requirement of a reversible heat transfer process is delta T between the system and the surrounding should be as small as possible. Whether the system remains isothermal or not, that is not the criteria. But if system remains isothermal, surrounding has to remain isothermal. Otherwise delta T, small delta T will not be maintained. So this is a very useful concept. So reversible isothermal process of heat addition. Next process is a reversible. When I will come to different cycle, then I will explain how the reversible heat addition through varying temperatures are possible. Reversible adiabatic. What is adiabatic? You know this terminology, adiabatic? No heat interaction. Very good. Adiabatic process is a process during which there is no heat interaction between the system and the surrounding. That means the entire boundary of the system is made insulated. Next is reversible adiabatic process of expansion, then reversible, same thing, isothermal process of, according to second law of thermodynamics, there should be a process of heat. Very good, because only adding heat one cannot get work in a continuous cyclic process. All the heats cannot be converted into work in a continuous cyclic process. Reversible isothermal process of heat rejection. What is the next one? Reversible, very good, reversible adiabatic process of compression. Now, therefore, we see that Carnot's engine comprises 4 reversible processes. It is a reversible engine. One is reversible isothermal process of heat addition, reversible adiabatic process of expansion, reversible isothermal process of heat rejection, reversible adiabatic process of compression. Expansion means where pressure is reduced, volume is increased. Compression means where pressure is increased and volume is reduced. So, 4 processes. Now, this is conceived in practice like this. Let us consider stages like that, a piston and cylinder, which is easy to conceive in practice, which contains a gas inside it at a temperature T1 and a pressure PA/VA, which refers to a state A. Temperature T1, I have not given the suffix A deliberately, T1, PA/VA, these are the properties. There may be many properties, you know, number of independent properties are fixed, other properties will be fixed. PVT are 3 fundamental properties, always that is why people represent with these 3 properties, 3 fundamental measurable properties at a state A. Now, what we do at this stage, we take a body or external heat source whose temperature is, it should be theoretically T1 for a reversible heat addition. First process is isothermal reversible heat addition, but it cannot be made. So, we take a very small dT1, where dT1 tending to 0. And what we do, we insulate all the lateral surfaces of the entire lateral surface of the piston, and you just make it close contact through a diathermic wall with its head, so that some amount of heat, let Q1 flows to it. Now, thing is that if you want to make an isothermal heat addition, whenever heat will be added, the temperature will go on increasing. So, to make this temperature constant so that an infinite small temperature difference always exists for a reversible heat transfer, we have to slowly push the piston so that the gas expands. That means as if heat is added, temperature is going to rise, and at the same time if you expand the gas slowly, the temperature will fall. That means it can make an adjustment of constant temperature process. Afterwards you will see for an ideal gas, internal energy is a function of temperature only. That means the amount of heat added is coming out as the amount of work done, so that the change in internal energy remains same, so that temperature remains same. But at this moment I think it is not proper to say that, because we are not sure that when the internal energy will remain same, temperature will remain same or not. But we can say that if you expand the gas in an adjusted manner, you can make it possible an isothermal process of heat addition. So that a stage B comes where the piston moves a little distance this side, and some amount of heat by that time is added to this at a constant temperature T1. So, this is the process A to B. So, therefore, what happens at this stage B here, the gas is at a T1. Now, I disconnect this, remove this heat source, and at different pressure PB and VB, because this gas has expanded, the gas has expanded, but during this time some amount of heat has been added. So, this is the state B. So, at this position the gas is at state B. I have not written that. That means this is the process A to B where the heat has been transferred. During this process isothermal heat addition has taken place. That means in this process I should have drawn this also. The body is there at T1 plus dT1. Now, at this moment what we do? We remove this and we insulate the entire, as if it was there insulation. That means what we do, we additionally insulate this front portion, the head of the cylinder. That means the total cylinder is insulated, and we make the piston also insulated. And then we allow the piston to expand, the large expansion process. In this way, the piston expands and comes to a stage C. For example, here, this is the stage C. Now, this is the stage C. That means when it comes here, the piston, this gas is at a different volume and pressure, which is PC and VC, which has not been shown here. Then what happens? The piston is again, then this insulation is okay. Then the piston is again brought in contact to another body or thermal reservoirs whose temperature is little less than the T2. T2 is the temperature at the state C, whose temperature is little, so that some heat is, T2 is dT2 tending to 0. And at the same time, for a heat rejection process to be isothermal, we will have to slowly move the piston this side, so the gas inside is compressed, so that if any cooling effect due to this rejection of heat is being counterweight and the temperature is maintained constant. So, the piston is moved slowly to some distance here. So, this is the end of this process CD, where the piston is at point D. Then this temperature remains still at T2. Then what we do? We just insulate the entire cylinder and remove this, well, reservoir, and again compress the gas to its initial state where it was. So, this state and this state is same. That means this is T1 PA VA. So, this is all insulated condition. Now, this case piston is also insulated. This is all insulated condition. Piston is insulated from the beginning. Only from one side the heat addition or heat rejection was taking place. Now, if we draw this diagram in a cyclic, in a thermodynamic coordinate diagram, this cyclic process, let us consider P as the ordinate and V. Now, you see, then it will be easier to understand. So, in the first process A to B, the system was at some state A here. This is an isothermal heat addition process. That means heat is added while temperature remains constant, and to maintain so the piston has to move outward little bit. That means gas has to expand little bit to counterweigh the heating effect of the gas. So, we can show qualitatively this curve like this. There is a little expansion. That's B is like this. This is the condition. This is the B. That means this is A, where this is PA VA coordinate, and this is B, where the coordinate is PB VB. Well, where PB is less than PA and VB is more than VA. Then there is an reversible adiabatic. Now, what is reversible adiabatic expansion? That means the piston has to move very slowly. Here the heat transfer process is also extremely slow, because the temperature gradient is infinite small, dT1 tending to 0. When you stop this, make the entire system insulated or adiabatic, then piston has to move very slowly outwards for the expansion process. Because why it is slow? To get rid of the mechanical friction as the mechanical dissipative effect. There is no heat transfer, there is no thermal dissipation or thermal irreversibility. So, it is free from irreversibility. That means very slow and quasi-equilibrium movement, as we have given the example. The piston moves as if there are a number of weights there, and if you slowly remove the weights, a small amount, in that case, in this case, what will happen? The piston will slowly move very gradually, so that each and every intermediate steps can be conceived of an equilibrium state, the quasi-equilibrium expansion. So, this can be represented by a steeper graph here C. We do not know the exact shape, we can only show the qualitative trend, because until and unless we know the equations between P and V, which we can only know if we know the property relations of the gas, otherwise we cannot find it, only qualitatively we can show. This is the process C. Then at C, what will happen? Again there will be a heat rejection at constant temperature. So, to do that, piston has to move outward, that means compress the gas to counterweigh any cooling effect of the gas to maintain an isothermal process of heat rejection. So this is a similar compression process which ends at D. So here the coordinate is PC, VC. Here the coordinate is PD, VD. That means this is the stage here when it comes from C to D here. Then from D to A, again a reversible compression, reversible adiabatic compression. So this ABCD represents this reversible cycle known as Carnot cycles in the PV diagram, which consists of two isothermal process. This is the isothermal process where the temperature remains T1. This is the isothermal process temperature. That means temperature at A and temperature at B is same and equals to T1. Temperature at C and temperature at D are same and equals to T2. Now what interesting thing is that here these two processes there is no heat interaction. So heat is only coming in this process by an amount Q1 and heat is being rejected in this process by an amount Q2. These two are the reversible isothermal process and there is no heat interaction. Q is 0. Q is equal to 0. That means these two processes are reversible adiabatic process. One is an expansion process, BC, another is a compression process, and these two processes are reversible isothermal process. So this way one can conceive of a reversible engine which was conceived first by Carnot, and it is known as Carnot's engines, which consists of two isothermal, reversible isothermal processes, one of heat addition, another of heat rejection, and two reversible adiabatic processes. And here also eta is equal to 1 minus Q2 by Q1, and that is equal to 1 minus, as we know the ratios like this. Now I will come to the very important concept of entropy, birth of entropy. Rather I will write like that, birth of entropy. Birth of entropy. How do you get it? Now we know that if there are two reservoirs at absolute temperature T1 and another at an absolute temperature T2, and if a reversible heat engine operates between these two temperatures taking heat Q1 and heat Q2, what we know? We know that in a cycle, cyclic process, this is the representation, Q1 by Q2 is equal to T1 by T. First I start with a very simple thing, Q1 by Q2, this we know because this is the definition of absolute scale of thermodynamic, absolute thermodynamic scale of temperature. We can write this Q1 by T1 minus Q2 by T2 is 0. Okay? Then we can write Q1 by T1 plus minus Q2. Why this way? Because Q2 is the heat rejection whose conventional sign is negative if we take heat addition as a positive. One as a positive, another as a negative. Otherwise how I will signify or imply the sign conventions. So convention is that this is positive, this is negative. So this can be written as sigma of this quantity over a cycle is 0, which can be written in this form. This is the cyclic integral, always we have done this earlier. The cyclic integral of dq by t is equal to 0. Is it clear? A very simple case where I consider a constant temperature thermal reservoir for heat addition, a constant temperature thermal reservoir for heat rejection, and from very simple case I can immediately conclude that cyclic integral dq by t is 0. This is nothing but the definition of absolute scale of thermodynamic temperature or absolute thermodynamic scale of temperature. So cyclic integral dq t is equal to 0. Now henceforth you will have to remember one thing, that if cyclic integral of any parameter is 0, here the parameter is dq by t. If cyclic integral of any parameter, this cyclic integral, look, this is for a reversible engine, so we will have to give a R. That means this represents a reversible engine, dq R. That means cyclic integral dqr by t. Many book gives this r here, that means to represent the cyclic integral of dq by t in a reversible cycle, because this is only valid for a reversible cycle. This equation I cannot use for any other cycle. So therefore, dqr by t, this quantity, I prefer to give it here, because why I am telling you, because I will be proving in a different way immediately, because today we do not have to prove in a very tortuous manner. So you know, whenever we have cyclic integral of any parameter is 0, we can express that parameter as a differential of a point function. Why? Because cyclic integral of a point function is a 0. So that if I define a point function s, so that the differential of this point functions is dqr by t. That means cyclic integral of any parameter is 0 means that parameter represents the differential of a point function, because differential of a point function is always 0. Cyclic integral of a differential of a point function is 0. So therefore, if I represent this dqr by t parameter as a differential of a point function s, then I can write ds is dqr by t by this analogy. Because since cyclic integral of this is 0, I know cyclic integral of any point function, differential of point function is also 0. So I can write this, so that point function can be written in this term, so that differential of this point function equals to this. Okay, this is the definition of the entropy. That means if we integrate this in an finite change of s point function, or this change in point function between two states will be 1 to t. First, I will not speak of entropy. I will tell a point function s, so that its differential equal to dqr by t, where dqr is what? Dqr is not a differentiable quantity. It is a infinite small amount of heat addition to a reversible engine. And if you divided it by t, it becomes a differentiable, which means mathematically 1 by t is acting as an integrating factor. Very good, as an integrating factor. That means 1 by t into dqr becomes ds, that is a point function. And if we express the finite change in this point function, we will integrate this side, simple school level mathematics. If I want to express this point function as a difference between the two specified states 2, 1, I will write the same thing with the limit 1, 2. This point function s is now I declare as entropy in my list of properties, because any point function is a property which is a state variable of a system. This way the first birth of entropy comes into picture. So therefore, the change of entropy is the quantity dqr by t in a reversible process, because all are valid for a reversible process. So therefore, this is the basic definition of entropy. Well, any problem? No problem. So I think time is almost over, so that I must stop it here.